Hello, IB Physics. Today we're going to be looking at some notes in your IB Physics binder. So you're going to want to find your IB Physics binder and find the Unit 3 tab and find 3.5. It's called Acceleration Time Graphs, another representation of motion. It looks like this. One piece of paper. We're going to look at both sides today in this set of notes. So you're going to want to find that and find some sort of writing utensil that you can use because we're going to be digging into this new representation of motion called an acceleration time graph. So last unit, we had looked at position time and velocity time graphs. We had looked at the situation where if I have an object that's like just you walking along the sidewalk or a ball rolling along the ground, we could look at its position time graph and then translate that into a velocity time graph. And what we found last unit was that that was pretty darn boring. That if I look at the slope of this line, this position time graph, I'm going to use slope to tell me what the velocity time graph is. It's going to be a flat, boring velocity. That means that the velocity is staying the same the whole time. So at every single time, at time 1, that's the velocity, still going at that velocity. At time 2, still the same velocity, still the same slope on this position time graph. So this is constant velocity motion. And we looked at that all last unit, unit 2. Unit 3, we're looking at changing velocities. In fact, things that are a constant acceleration. So acceleration, like you learned in your last assignment, is for when there's a changing velocity. So that would look on a position time graph like a slopey graph, like that. That's a slopey graph. Our lab looked a little bit like that, kind of like parabola-y shaped. But it's slopey, it's curved in our position time graph. And what that tells us is that the slope of this position time graph is actually changing the whole time. So actually, its velocity time graph would look something like that. It would tell us that the velocity is increasing the whole time. So today we're going to extend this understanding you have of velocity time graphs to a new type of graph called an acceleration time graph. And again, acceleration is how fast the velocity is changing, the rate at which the velocity is changing. And so we're going to think about, well, how do I go from a velocity time graph to an acceleration time graph, and how do I go the other way around? And so we're going to go ahead and start out on our notes sheet with example 1. And here is example 1. Mine is a little bit larger than yours, but they're pretty much the same. And I want to think about, how do I know what the acceleration is in each section? Like, how could I find that? Considering the idea that acceleration is looking at the change in velocity. So take a moment, think about that. Well, if acceleration is change in velocity over time, it's the rate that velocity is changing, I could look at the change in the velocity right here and then look at how much time that has happened over. It looks like 3 seconds. So I can go ahead and say, okay, well, that happened, a change in velocity of from 1 meters per second up to 4 meters per second. So 1 to 4 meters per second is plus 3 meters per second. And then I have to divide it by the amount of time that happened in, which is 3 seconds. And I'm dividing them, so I'm going to do this in this sort of inconvenient way. That's a division sign, clearly. And then 3 divided by 3, well, that equals 1. So equals 1. And take a moment and think for yourself, what would the units be here? So I've got 3 meters per second divided by seconds. You might be like, oh, the seconds will cancel out, but they won't actually cancel out because these seconds are in the denominator. I know they're in the numerator, but they're in the denominator. These seconds are in the denominator. So what I actually have is meters per second. Oop, nope, that is not a hotkey here. Per second, or per second squared. That's a really unattractive way to write squared. So we know that the acceleration, or the rate that the velocity is changing, is 1 meter per second squared. Or you could write this as 1 meter per second per second. They're both the same thing. There's seconds in the denominator twice. More commonly, you're going to see meters per second squared, but meters per second I think is kind of a nice way to understand that it's telling you that for every second, we're going to be going 1 meter per second faster. So that's my acceleration for section 1. Take a moment right now and try calculating your acceleration for section 2. Notice that I looked at the change in velocity over the amount of time that change happened, which is actually just looking at the slope. So you might want to pause the video and go ahead and calculate for section 2. No, really, like pause the video. Do the calculation. You got this. And maybe you realize that this calculation is pretty easy because this is a flat line. So the slope for section 2, well, that's a flat line, which means that the acceleration is equal to 0 meters per second per second. Kind of boring. I agree. So we can go ahead and graph those two things. We can also take a moment and calculate for section 3. So you go on ahead and pause the video if you're feeling like, yeah, I can find the acceleration for section 3. That's just looking at the slope of the line. And if you're like, oh, I'm not really sure yet, keep watching my video. I'll help you out. So one way I could do this is that I could actually like count the boxes and look at the rise over the run. But I'm going to tell you that sometimes that is pretty inconvenient. That makes life a little bit hard because, as some of you have noticed, sometimes the points aren't the boxes aren't evenly spaced. So what I'm actually going to do is use point slope formula to say, well, what is this point right here? Right there, that is over 5 seconds and up 4 meters per second. So I know one point, and then I need to find another point to find the slope. So that's this point right here. I'm going to put the 5 meters per second right on it. I need to find another point. Oh, I don't know if this is still recording. Intriguing. Hope it is. I need to find another point. And so you might be like, oh, great, let's just do the last point. Because like the last point would be easy, right? And I'm with you, the last point would be easy, but there's an easier point that we could use. Notice that we cross the x-axis. So I'm going to use that point because I think it's even easier. That's going to be right here where the line goes through the x-axis. And the reason that that's easier to me is that it includes the number 0. So at 7 seconds, we are going 0 meters per second. So at that moment in time, the velocity is 0 meters per second. So then I'm going to go ahead and take those 2 points and use point slope formula to help me calculate my slope for this section. Yep, I did it wrong. Guys, when you're doing point slope formula, the y value should go on the top. I just deleted a bunch of video, but I think you're going to track what happens. So I did my y value, y1 minus y2. So that's 4 meters per second divided by minus 0 meters per second. So that's the change in velocity. Then I'm going to divide by time. Man, it's a hard life. I didn't do that the first time. So I have the x's on the bottom, so that's 5 seconds minus 7 seconds. And you might be complaining, like, Ms. Getz, you're doing it backwards. And while I was doing it wrong when I abruptly changed this video, it doesn't actually matter whether you do the y1 points first or the y2. It doesn't matter which order as long as you keep it consistent. So if you did 0 minus 4 meters per second and then 7 seconds minus 5 seconds, we're going to get the same answer. And that answer is that it's 4 meters per second divided by 2. So 4 divided by 2 is going to give me 2. And then my units are meters per second, or meters per second squared, neither of which fits very well here. Let's move this text box on over. And you should point out, Ms. Katz, you forgot something important. There's a negative sign here. That negative sign is really important, and it's telling us that the acceleration is obviously negative. And so I have my acceleration now for section 3 is negative 2 meters per second squared. Yay! And so I'm going to graph those. So section 1 I found was positive 1 meters per second squared. Notice this is written in IB format. It has a negative 2 in the exponent, and that's indicating that it's in the denominator. For section 2, 0 meters per second squared. Pretty boring, not accelerating. That means that the velocity is constant at this time. And then for section 3, we have an acceleration of negative 2. So it's a negative acceleration. We can tell because this is clearly a negative slope. Negative 2 meters per second squared. Awesome. So hopefully you've jotted this down along with your work on 3.5 on your notes sheet. And so what we're noticing here is that to get from a velocity time graph to an acceleration time graph, we're using the slope. And this should make a lot of sense to us because it's kind of the same process that we used to go from a position time graph to a velocity time graph. So notice that there's a lot of symmetry here. We use the slope, and then we use the slope again as we are moving to more and more complex graphs. So what I'd like you to do right now is go ahead and try creating your acceleration time graph for example 2. So go ahead, the video is going to stop, so you don't need to even pause it. Determine your accelerations for each point and plot your graph. Please actually take a moment to plot your graph here for the acceleration time graph for this particular example. So notice that our object's velocity is undergoing a lot of change. This is actually going to be a pretty hard graph to describe the motion of. But all I need you to do right now is determine the acceleration time graph. Good luck. You can do it.